So what if I told you an attacker could hijack your computer, but without writing a single line of their own malicious code? Sounds kind of wild, right? Well, they can do it by just cleverly rearranging the instructions your own program uses every day. This is a real technique. It's called return-oriented programming, or ROP for short, and it basically turns your software into its own worst enemy.
All right, so here's how we're going to tackle this. First up, we'll get into the why, like what problem does ROP even solve for an attacker? Then we'll dive into the how, really looking at the nitty-gritty of hijacking a program. From there, we'll actually build our very first attack. Then we'll level it up by chaining actions together. And finally, we'll see how modern tools automate this whole thing, making it a serious real-world threat.
Okay, so to really get ROP, we first need to understand the big problem it was designed to solve. Think of it as a kind of malicious recycling. Or, as you're about to see, it's a lot like putting together a ransom note.
So for years, the classic attack was pretty straightforward. You just inject your own nasty code into a program's memory and then trick the program into running it. Simple. But modern systems got wise to this. They introduced a really powerful defense, you might have heard of it, the NX bit, or executable space protection. Basically, it marks certain areas of memory, like the stack, as data only. You can write to it, sure, but you absolutely cannot execute code from there. And just like that, a whole class of attacks just vanished. So the question for hackers became, well, how do you run your code if you can't inject any code?
And the answer is just brilliant. If you can't bring your own code to the party, well, you just use the code that's already there. This is where that ransom note analogy really clicks. You're not writing a new message from scratch. Instead, you're finding existing letters and words in a newspaper, or in our case, tiny snippets of code that are already in the program's memory, and you're piecing them together to say something totally new and totally malicious. You are literally using the program's own vocabulary against. So let's put a formal name on this. Return-oriented programming, or ROP, doesn't inject any new code. What it does is hijack something called the control flow, that's just the path the program takes while it's running. It completely derails that path and forces it to jump between these little pre-existing code snippets. And we call those snippets gadgets. Remember that term? Gadgets. They are the key to this whole thing.
So, how is this hijacking even possible? Well, the entire exploit hinges on one critical and honestly pretty fragile part of every single running program, the call stack. Okay, remember that NX bit? It stops us from executing code on the stack. So the new game plan isn't to put new code on the stack, but to corrupt the data that's already there. And the main target is the return address. You can think of the return address like a sticky note a function leaves for itself that says, hey, when I'm done with my job, go back to this exact spot. Now, if an attacker can sneak in and just scribble a new address on that sticky note, they get to decide where the program goes next.
And this slide shows you exactly how that works. On the left, you've got normal, happy operation. Data fits nicely into its little box, the buffer, and that all-important return address right below it is safe and sound. But now, look at the right. This is a stack overflow. The attacker just sends way too much data. It spills right out of the buffer and just bulldozes everything after it, including that critical return address. All of a sudden, that go back here sticky note has been completely replaced.
And this right here, this is the attacker's big aha moment. So to test for this vulnerability, they'll just try to crash the program by sending a super long string of the letter A. Then they look at the instruction pointer, the EIP, which tells the CPU what to run next. And what do they find in it? The hex value 41414141. Now that is not some random address. That is the ASCII code for AAAAA. This is the smoking gun. It is absolute proof that the data they sent has successfully hijacked the program's control flow.
So the objective now, it's not just to crash the program anymore. The goal is all about precision. Instead of overwriting that return address with junk A's, you override it with the actual memory address of a useful piece of code that's already loaded in memory, something like a function from a standard library.
Okay, so with that in mind, let's build our first real attack. The classic starting point for this is an exploit called Return to Liebeck. And just like the name suggests, what we're going to do is redirect the program to a useful function that's inside a standard C library, which, by the way, is almost always loaded into a program's memory.
Crafting the payload for this is like assembling a very, very precise package. As you can see here, it's got 4 main parts. First, you have the padding. That's just enough junk data to fill up the buffer and land exactly on the return address. Second, you swap out that original address with the address of the function you want to call, something juicy like system. Third, you need a dummy address for where system should go when it's done.
And finally, you put the argument for your function, in this case, a pointer to the string /bin/sh. Now, of course, this isn't just guesswork. To build this payload, the attacker really has to do their homework. They need to find 3 key pieces of information: the exact memory address of that system function, the address of the string /bin/sh, and most importantly, they have to calculate the precise offset, the exact number of padding bytes they need to hit their target without over or undershooting.
So what happens when the vulnerable program gets this payload? Well, the function finishes its job, it tries to return, but instead of going back where it's supposed to, it gets redirected. It jumps straight to the system function. The system function then looks at the stack for its argument, finds our address for /bin/sh, and boom, it executes it. And just like that, the program, doing exactly what it was told, opens up a command shell for the attacker. Game over.
Okay, so getting a shell is huge, right? But what if you want to do more? What if you need to perform multiple steps? This is where the return-oriented part of the name really starts to make sense. We're going to chain multiple actions together.
So here's the next challenge for us. Calling one function is great, but a real attack is often more complex. It requires a sequence of steps. So how do you make the program call one function, clean itself up, and then immediately call a second function that you've also chosen?
The answer is to use these things called gadgets. Now, a gadget isn't a full function. It's just a tiny sequence of useful machine instructions that just so happens to already exist somewhere in the program's code. But the one critical thing that every gadget must have is a ret, a return instruction at the very end. That final ret is the engine that drives the whole ROP chain. It's what lets us jump from the end of one gadget to the beginning of the next one.
Now, the quintessential gadget, the one that attackers are always on the lookout for, is the pop ret sequence. It does 2 very simple but absolutely critical things. The pop instruction just grabs whatever's on the top of the stack and throws it away, perfect for cleaning up old arguments from a function we just finished calling. Then, the ret instruction takes the new item at the top of the stack and jumps to that address. So it cleans up, and then it continues the chain.
All right, let's actually trace this flow on the slide, step by step. So our initial overflow points the program to our first function, let's say printf. Once printf is done, it hits its return instruction. But where does it return to? Well, it returns to the next address we put in our payload, which points to our handy pop ret gadget. The gadget runs, the pop instruction gets rid of the argument we used for printf, cleaning up the stack. Then, the ret instruction grabs the next address from our payload, which is the address of system call, and jumps right to it. See that? We just seamlessly chained a printf call right into a system call.
And you can just keep doing this over and over. By carefully stacking up a list of addresses, pointing to functions and gadgets in a very specific order, an attacker can build what we call a ROP chain. It's basically a brand new, malicious program built entirely from the spare parts of the original software.
Now, I know what you're thinking. This all sounds incredibly complex to do by hand, and you'd be right. It is. Which is why, in the real world, attackers don't. They use specialized tools to automate this whole process.
I mean, just finding these gadgets and calculating all the addresses manually is tedious enough. But modern systems have another powerful defense called address space layout randomization, or ASLR. You can think of it like shuffling a deck of cards. Every single time the program runs, the memory addresses for all the code and libraries are in a different place. So an address for a gadget that worked perfectly one time will be completely wrong the next time you run it. This makes trying to exploit things manually a really frustrating game of chance.
And this is where automation becomes a game changer. You have tools like ROP that can instantly scan a program and just give an attacker a complete menu of every single available gadget. And then you have these incredibly powerful frameworks like PyTools, which can act like a master chef. It automates everything, finding the vulnerability, calculating the exact offset, discovering all the addresses it needs, often by first leaking some information to figure out where ASLR put everything, and then building the entire complex ROP chain payload for you automatically.
And this really leaves us with a pretty profound question, doesn't it? Return-oriented programming really challenges our most basic assumptions about security. I mean, if an attacker never even needs to introduce their own code and can instead just use the program's own building blocks to create malicious behavior, it kind of forces us to rethink what it truly means to write secure software in the first place.